Hello. So, the fundamental theorem of algebra, which we alluded to in the last video, says that an nth degree polynomial has n roots. Okay, and we talked about how the multiplicity here comes into play, and that even if a root, it looks like there's only one of them, it might be counted several times. And here's an example. So let's pretend I have this function here. This is a parabola, quadratic. Okay, so a typical quadratic has two roots. So in this case, n is equal to 2. Okay, that's a second degree polynomial. Okay, there's two roots. We got one right there. We have a second one right there. Okay, well, if I have a parabola that has only one root, it might have something like this. And so, wait, sorry, that's one real root there. That's the first real root. And here we have the second real root. Okie dokie. In this case, we have really just the one real root, so that's the first one. But remember that this one would have multiplicity of 2. So an example of this function could be, well, x squared. Well, I guess the function is kind of moved over. I'll say it's x minus 1 squared. And so the first real root actually has multiplicity of 2 because it occurs twice. That would be written as x minus 1, and so you have the first one and then the second one. So that's why we would still say it has two roots, even if they're not unique. Okay, so I'll underline that there. That might help. These roots need not be unique or distinct. Distinct is a word that comes up a lot, so we'll use that as well. Okay. But there is another possibility when it comes to quadratic functions anyway, and that could be like this. So an example of this function could be something like x squared plus 3. Wait, let's not do something like that. Let's do x squared plus 9. Okay, where, okay, there are no real roots, right? We've seen this before in talking about quadratics. So this is a function that has no real roots. No real roots. Okay, if you've been paying close attention, I've been specifically saying roots and then leaving out or putting in the word real. And I haven't been lying to you. This graph indeed has no real roots. We can quite clearly see that there's no x value, no real x value, where when I plug it in, y is going to equal 0. Again, I'm talking about this function right here. But look at the fundamental theorem of algebra. It only says that there are n roots. It doesn't say anything about whether the roots are real or not. And so you're gonna have to kind of wrap your brain back, and I apologize for doing this to you, but think back to when we talked about quadratics. Actually, did we talk about this when we were talking about quadratics? We might have left it out this year. Anywho, we have to open our mind beyond just real numbers now. And so let's actually see an example of this. Alrighty, so again, this function has no real roots, and we're going to see an example of that and what that looks like. So here's such an example. I have x squared minus 4x plus 13. You can take a second and try to factor it, and I believe it is actually not factorable using real numbers and real coefficients anyway. So let's actually use the quadratic formula to find the roots. Okay, so let's find the roots of this function. Again, so what that would mean for a quadratic anyway is set the y value equal to 0, and since I don't know if it's even factorable or not, I'm going to use, and I could check the discriminant, but I'm going to use the quadratic formula. So that's going to mean that x is equal to negative b, so that'd be, negative 4, or positive 4, plus or minus the square root of, I like to use parentheses here so we don't mess up, times 4 times 1 times 13. All over 2a, so that would just be 2 times 1. Okay, so check my work here, but I believe this should end up being 4 plus or minus the square root of, let's see, 16 minus, let's see, 52 is going to equal negative 36. Okay, so the discriminant is negative 36, which is not a perfect square, and therefore it wasn't factorable, as expected. Whew, okay, so now I have that divided by 2. Now at this moment, if you say that has no solutions, you're almost right. So again, this has no real solutions because again, we can't take the square root of a negative number. But this is where this comes into play, and the idea of complex numbers. And this is definitely something you're going to jump deeper into as you go on in your math career. But we want to kind of actually get an answer out of this. I don't want to leave it to say, oh, it's just no answer and be done with it. Because complex numbers actually come up in a number of ways in the future. Won't quite get into that right now. But the idea here between a complex number is, well, we have to figure out what an imaginary number is. And the basis of all imaginary numbers is this guy called I. And the definition of I is some magical number that when you square it is equal to -1. We call I the imaginary unit. Remember. And again, I'm kind of going over this because it's been a while. Call it the imaginary unit. It's the basis of all these imaginary numbers. And so, just like on the real number line, we have this. We have 0, then we have 1, 2, etc. And negative numbers as well. The imaginary number line just looks like this. There's I, there's 2i, 3i, and so on. And going backwards, there would be 0i, negative 1i, negative 2i, and so on backwards. Okay, oops, sorry about that. Right there. Okay, that's unnecessary right now though. So what does this actually mean? This means that if I was to actually take the square root of this, we actually could, because I can write this like 36 times -1 over 2. And one of the nice things about square roots is that if I can split the inside up into a product, I can just take the square root of each factor individually. And so the square root of 36 is 6. So I have 6 there. And the square root of -1 is I. Like so. Over 2. And I could divide this now, and I'll just get 2 plus or minus 3i. So I have two solutions here. Now, let's actually do a little bit more cleaning up. So x could be equal to 2 plus 3i. Or, and again, the second solution is 2 minus 3i. Alrighty. So these folks, individually, these are called complex numbers. The definition of a complex number is really just some real part, some real number, plus an imaginary part. So the real part is the part in front without the I. Real is, and then the imaginary part is the part with the I. What's nice about this, and what's really interesting, is that with these complex numbers, and when we're dealing with how they come out as solutions to quadratics that maybe don't have real solutions, notice that every time you do this, you're going to have 2 plus 3i and 2 minus 3i, or 5 plus 7i and 5 minus 7i. So more specifically, these two are complex conjugates. It's a fancy word we have. Complex conjugates. Okay. If you're still a little unclear about what the where these complex numbers come from and how to work with them, don't worry. You're going to have time to kind of just handle them on their own without any context, just to get used to them and get a nice hold of them. But we come back here. So this function right here, it has no real roots. It has no real roots. But it does have, but no real roots, but has two, we say, complex roots. And that is where the fundamental theorem of algebra comes into play. And so it is still following this theorem, because there are 0 here plus 2 here. 0 plus 2 is indeed 2, as stated here. Alrighty. So thanks for watching. We'll have a couple more videos, or I probably won't make them. I'll probably find some much better videos for you to see what complex numbers are and how to work with them once again. Alrighty. So thanks for watching, and I'll see you later.